Welcome to my channel. In this video, I will explain Laurent Theorem, which is a very important topic in complex analysis. In the last video, I have explained Taylor's theorem, where we have seen if we have an analytic function fz in a domain D, there the function can be expanded in Taylor series with respect to any point z0 in D. Now, if we have the function fz which is not analytic at some point z0 or which is not defined at the point z0, then also we can get some expansion of the function fz about the point z0. But in this case, we'll get Laurent series expansion. So let us go to the theorem. So Laurent theorem says, if fz be analytic in an annular region denoted by a z0 r1 r2, then for any z in the annular region, fz has a unique representation in this form. Now this can be written in two parts. The first part is called principal part, whereas the second part is called analytic part or Taylor's part of the function fz. Now the coefficient can be determined from this expression, which is given by 1 by 2 pi I integral over c fz dz by z minus z0 power n plus 1. Now what is c? C is the closed Jordan curve which is inside the annular region. Now, what is called an annular region? So let us see, which is denoted by a z0 r1 r2. So here we are taking a point z0 in the complex plane, and the first circle with center z0 and radius capital R1 is this one. So this is a circle with center z0 and radius R1. Next, let us take another circle with center z0 and radius R2. So this is the circle with center z0 and radius R2. So between these two circles, the first one is C1, it is z minus z0 is equal to R1, and C2, it is z minus z0 is equal to R2. So between these two circles, this region is called annular region. So if the function fz is analytic in this region, this tire-shaped region between these two circles, then fz can be expanded with respect to the point z0, which is not inside the region in the Laurent series expansion. Okay, now this annulus region, this is a typical annulus region. Every time we will not get this kinds of figure. Okay, rather, so if I take r1 equal to 0, in this case you will see, so r1 equal to 0 means this is a circle with center z0 and radius 0. That means it is a point. Okay, this is a punctured disk we are getting. So this is the circle with center z0 and radius r2, and r1 is 0. Okay, that means the function fz is analytic in this part. Okay, so here the function fz is analytic inside this region except the point z0. Okay, this is an annulus region. Similarly, so this is the circle C2. Okay, so the function fz is analytic in C2 except the point z0. Now if r2 is equal to infinity, that means the second circle, the larger one, is a circle with center z0 and radius infinity. So in this case, the function is analytic in this region. So except this circle, inside this circle, this region, the function is everywhere analytic. So this is circle with center z0 and radius r1. So here the function is not analytic, but it is analytic in this region. So this is also an annulus region. Another possibility, if both these two cases happens, that means if r1 equal to 0 and r2 equal to infinity. So in this case, you see, so here the function fz is not analytic only at the point z0, but it is analytic everywhere in the entire complex plane. So except z equal to z0, the function is everywhere analytic. So these are the four possible cases we have where we can expand fz in Laurent expansion with respect to the point z0. Now, another important point about Laurent expansion, you see, if the coefficients of all z minus z0 power minus n, that means a minus n are zeros, then fz becomes, so if a minus n are all zeros for all n, then fz becomes summation n equal to 0 to infinity a n z minus z0 power n. Okay, so which is the Taylor's expansion? That means Laurent series can be reduced to Taylor's expansion if a minus of n, all the coefficients of negative powers are zeros, then we are getting Taylor's expansion. So let's continue with some good examples. So let us take fz equal to z by z minus 1, 2 minus z. What are the regions given? You see, it is mod z strictly less than 1, then 1 less than mod z less than 2, mod z is strictly greater than 2, and 0 less than mod z minus 2 less than 1. Okay, now we want to expand the function fz. Now you see here, this is the Laurent expansion, but every time to write Laurent expansion, we are not going to use this expression of n. Rather, we'll manipulate using some geometric series, some known geometric series, or some other standard expansions to get Laurent expansion, as we have done in the Taylor's series expansion. Okay, so here, so first our task is to simplify fz. So here you can see z minus 1, 2 minus z can be written as okay. So this is equal to now here if we put z is equal to 2, we'll get two equal to b times 2 minus of 1. So we are getting b is equal to 2. Okay. Next, if we put z is equal to 1 here, then we'll get 1 is equal to a times 1 minus of 2. So a is equal to minus of 1. So our function fz becomes z minus 1 plus 1 by plus 2 by z minus of 2. Okay. Now we have to expand this in the region mod z strictly less than 1. So what is this? So this is the circle with center 0 and radius 1, right? So we are going to expand with respect to the point 0, and this is strictly less than 1, right? And the function fz is getting its singularities at the point 1, 0 and at the point 2, 0. Okay, so both the singularities are not inside the domain. So you can see we are going to get a Taylor series expansion over here because the function is analytic inside this region mod z strictly less than 1. So let us see what happens. So mod z is strictly less than 1. That is the first case. So here we'll utilize this given information together with the expansions 1 plus z power minus 1, that is equal to minus 1 power n z power n, or 1 minus z power minus 1, which is given by z power n. Both are valid in the region mod z less than 1. Okay. Now this can be written as 1 by 1 minus of z. Now, so mod z less than 1. So mod z is also less than 2, right? So I can write this as mod of z by 2 less than 1. Okay. So this can be written as 2 by minus of 2, 1 by 1 minus z by 2, right? So here we are getting 1 minus z power minus of 1 minus of 1 minus z by 2 power minus of 1. So this can be written as, so using this expansion we are getting z power n, and here we are getting z power n by 2 power n. So the expansion is equal to 0 to infinity 1 minus 1 by 2 power n z power n. Okay, so here you can say this is of Taylor's form. No negative power is present over here, right? So in this region we are getting a Taylor's expansion. Next, let us go into the next region, that is between 1 and 2, which is an annular region, right? So fz equal to case 2 1 less than mod z less than 2, and our fz is 1 by 1 minus z plus 2 by z minus of 2. So now mod z is strictly greater than 1, right? So here we can see 1 by mod z strictly less than 1. So we have to make it 1 by mod z. Okay. So 1 by z. So let us take z here. So in that case, you will get 1 by 1, 1 minus of 1 by z. Okay. If you take minus of z, we'll get 1 minus of 1 by z plus, in the next case, what happens? Mod z is less than 2. So here we can write z by 2 is less than 1. Okay. So here we'll take 2. We'll take minus of 2 and we are going to get z by 2. So it is minus of 1 by z, 1 minus 1 by z power minus of 1, minus of 1 minus z by 2 power minus of 1. So it is 1 by z, it is 1 by z power n equal to 0 to infinity, and minus of z power n by 2 power n. So if we simplify, we'll get this as minus of 1 by z power n plus 1 minus of 1 by 2 power n into z power n, right? So here you can see this is the Taylor's part. So this is the analytic, this is the principal part we are getting, which contains all the negative powers, and this is the analytic part or the Taylor's part, where this is the coefficient of all the positive powers, and these are what are the coefficients of the negative powers. It is minus of 1. Okay, so let us go into this third case, which is in the region mod z strictly greater than 2. So if mod z is strictly greater than 2, so what is our fz given? Fz is equal to 1 by z minus of 1 1 minus of z plus 2 by z minus of 2. So we have to utilize this information, that is mod z is strictly greater than 2. So if mod z is strictly greater than 2, so we can write this as 2 by z is strictly less than 1. So we have to make it 2 by z strictly less than 1. Okay. Now what about this 1 minus of z? Now since mod z is strictly greater than 2, so mod z is strictly greater than 1 also, right? So here also we can write 1 by mod z is strictly less than 1. So in both the cases, so we'll take minus of 1 by z, and here we'll get 1 minus of 1 by z. So here also we'll take plus 2 by 2 by z, right? 1 minus of 2 by z. So this can be written as 1 minus of 1 by z power minus of 1 plus 2 by z, 1 minus 2 pi z power minus of 1. Here we'll get, so it is n equal to 0 to infinity 1 by z power n plus 2 by z n equal to 0 to infinity 2 power n by z power n. So we are getting 1 by z power n plus 1 plus 2 power n plus 1 by z power n plus 1, okay, which can be written as 2 power n plus 1 minus of 1 by z power n plus 1. So this is the Laurent series we are getting. So in this region, mod z is strictly greater than 2. Okay. So here we are expanding this annulus region, mod z greater than 2. We have expanded the function. Okay, next, what about the fourth case? In the fourth case, we have 0 less than z minus 2 less than 1. Okay. So that means, what is our fz? Fz is 1 by 1 minus of z plus 2 by z minus of 2. Okay. Now, the region is mod of z minus 2 is strictly less than 1. Okay. So, we have to expand with respect to the point 2, right? So, here z0 is 2. So, we are going to expand with respect to 2. That means we are going to generate this kinds of expressions. An z minus 2 power n equal to minus infinity to plus infinity. Okay. So here we have to express the terms in the powers of z minus 2. So here it is z minus 2. So we have to consider this case. So 1 by 1 minus of z can be written as minus of 1 minus of z minus 2. Okay. It's 2 by z minus of 2. So here, so mod of z minus 2 is strictly less than 1, right? Okay. So it is minus of 1 plus z minus 2 power minus of 1, okay, plus 2 by z minus of 2. It is expanded as n equal to 0 to infinity minus 1 power n z minus 2 power n plus 2 by z minus 2. Okay, so this is the expansion we are getting. So n equal to 0 to infinity, it is minus 1 power n plus 1 z minus 2 power n, which is the analytic part. all the positive powers of z minus 2 plus 2 by z minus 2. So this is the principal part which contains the negative power of z minus 2. Next, let us take another example. Say fz equal to z square minus of 6z minus of 1 divided by z minus 1, z minus 3 to z plus 2. Okay, so we have to expand this in the region 3 less than z plus 2 less than 5. Okay, first we'll break it in partial fractions. So this can be written as a by z minus of 1 plus b by z minus of 3 plus c by z plus 2. Okay, so here we have a times z minus 3 into z plus 2 plus b times z minus 1 into z plus 2 and c times z minus 1 into z minus 3. So here if you put z is equal to 1, we'll get 1 minus 6 minus 1, that is equal to, this part is 0, this part is also 0, we are getting 1, 1 minus of 3, 1 plus 2, so it is a is equal to 1. Okay, so from here we are getting a is equal to 1. So next, for z equal to 2 or z equal to, we get fz as 1 by z minus of 1 minus of 1 by z minus of 3 minus 1 by z plus 2. So we have to expand this in the annular region 3 less than mod z plus 2 less than 5. Okay, so what is this annular region? So this is the region between the circles C1. C1 is z minus of minus 2 is equal to 3, centered at minus of 2, radius 3, and C2, the large circle, is z minus of minus 2, that is equal to 5. Okay, so these are the circles. So let us try to draw the region. It is minus of 1 0, it is minus of 2 0, it is minus of 3 0, minus of 4 0, 5 0, here it is minus of 6 0 and minus of 7 0. Now it is centered at minus of 2, okay, with radius 3. So the first circle is, so this is our C1, centered at minus of 2 0 and radius 3. The next circle is a circle with center minus of 2 0 and radius 5, right? Okay, so this is the circle we have. So here we have C1 and this is our C2 and this is the annular region we have. So here we have to expand, right? So this is our annular region minus 2 R1 is 3 and R2 is 5. That is equal to set of all z such that 3 less than z plus 2 less than of 5. Right? So here we are going to expand the function and you will see you are getting a Laurent expansion. Okay. So the function fz is 1 by z minus of 1 minus of 1 by z minus of 3 and 1 by z plus 2. In the region 3 less than mod z plus 2 less than 5. So here you can see we have to write the expansion in terms of z plus 2. Okay, the powers of z plus 2 will be generated. So this can be written as z plus 2 minus of 3. Okay, next this can be written as z plus 2 minus of 5, and here we have 1 by z plus 2, so it remains unaltered. Now here you see z plus 2 is strictly greater than 3. So from here I can write 3 by z plus 2 is strictly less than 1, so that we can use the geometric series. So here we'll take 1 by minus of 3, 1 by z plus 2, and this becomes 1 minus 3 by z plus 2. Here we'll see z plus 2 is strictly less than 5. So from here we can write z plus 2 by 5 is strictly less than 1, right? So here we'll take minus of 5. If I take minus of 5, this becomes 1 by 1 minus of z plus 2 by 5. Okay. So now we can write this as z plus 2 1 minus 3 by z plus 2 power minus of 1 plus 1 by 5 1 minus z plus 2 by 5 power minus of 1, right? Minus 1 by z plus 2. So this expansion is 1 by z plus 2 3 power n by z plus 2 power n equal to 0 to infinity, and here we are getting z plus 2 by 5 power n minus of z plus 2. So you can see our principal part is minus of 1 by z plus 2 plus 3 power n 1 by z plus 2 power n plus 1. So this is the principal part. That means all the negative powers of z plus 2 and the positive powers of z plus 2. That means the analytic part is given by 1 by 5 power n plus 1. This is the coefficient, and z plus 2 power n. Okay, this is the analytic part and this is the principal part of the function fz of the Laurent series expansion of fz about the point minus of 2.